Sorry guys, I know that it's really awkward to watch a video of me doing a lecture, but that's kind of how today has to go. We need to keep moving forward and not present. Therefore, this is the solution to that problem. The solutions to the homework are will be here. Okay, I'll put them on the back bulletin board as usual, so you can check your answers. But in addition to that, there are some select problems that I think I would like to go over with you a little bit more detail, a little bit more depth. And so we're going to go over some of these problems together right now, and then the rest, if you are still struggling, you can't figure out with my solutions, you can come and talk to me at a later time. Okay, so the first one I want to do is number 24. Number 24 is, I think, the first one requires explanation. 19 and 22 are not necessarily super easy, but if you look at what I've done, I think that in itself is its own explanation. Number 24 says, in February 1955, a paratrooper fell 370 meters from an airplane without being able to open his chute, land in snow, suffering only minor injuries. Assume that his speed at impact was 56 meters per second, that his mass was 85 kilograms, and that the magnitude of the force on him from the snow was the survivable limit of 1.2 times 10 to the 50 degrees. Okay, so let's write down some of the stuff here. So we've got his mass is 85 kilograms. And the distance that he fell is 370 meters, which ends up being irrelevant, so I'm just going to skip that. And then his initial velocity when he hits the snow is 56, and his final velocity is 0, right? That's what happens. The snow brought him to rest. And then it says the force that he experienced was 1.2 times 10 to the 5th. So the first question asks for the minimum depth of snow that would have stopped him with this force, and the second is what is the impulse on him from the snow. This isn't even really a momentum problem. The impulse part of it is the momentum part, and it's like the easiest part. But the first part is actually a work problem. You're looking for a force that's acting over a distance that's creating a change in kinetic energy, and so you end up using the work kinetic energy theorem. Net work is equal to change in kinetic energy. And so the net work is going to be, you've got a constant force being applied over some distance, and the two things is going to be just a negative multiplication because it's f delta x cosine of theta. The force from the snow is up, the displacement is down, so theta is 180, cosine of 180 is negative 1. And then the change in kinetic energy is going to be the 1/2 and the final squared minus 1/2 the initial. This goes away to 0, so then you have 1.2 times 10 to the 5th times delta x equals 1/2 times 85 times 50. And for that answer, I got 1.11 meters. That's part A. Part B, that's the impulse, and that is the change momentum, which is mv final minus mv initial, and that is 85 times 0 minus 85 times 56, and I got negative 47 for that. Okay. Number 35 is the next one that I will do. And I'm not going to do the whole thing. I'm just going to say that the area under the curve is the impulse, and that is equal to the change in momentum of the ball. The change in the momentum of the ball is 0, okay, because it's changing direction. Even though it's rebounding with the same exact speed, the velocity is now changing direction. So if you think about the area under the curve, which is the integral of f dt, that's given to you in the problem. But then you say that's equal to the impulse, which is the change in momentum, or mv final minus mv initial. Okay, and if let's just say, let's pick one of them to be negative, we could say the initial velocity is negative, then it's 0.058 times 34 minus 0.058 times negative 34. And those two things don't cancel out. Okay, so then you can use that to solve for whatever your maximum force is from the graph. Okay, so I'm not going to do the whole problem, but that's how you would do that part of the problem. 37. 37 is a tough question, and I want to do the whole thing with you. A soccer player kicks a ball of mass 0.45 kilograms that is initially at rest. Okay, so we've got mass is 0.45 kilograms, and initial velocity is 0. And it says for 3 times 10 to the negative 3 seconds. So the time of contact is 3 times 10 to the negative 3 seconds. And they give you a force function of time. So the force is 6 times 10 to the 6 t minus. So the first thing you should think is this is not a constant force. So whatever I'm going to do is probably going to use calculus. Hopefully that's the first thing you think. That's the first thing I think. And it says find the magnitude of the impulse on the ball due to the kick. So the first thing it's asking is what is the impulse? Okay, well the impulse, the equation for impulse is the integral of f dt, right, delta p or impulse, same thing, is equal to the integral of f dt during the kick. So the kick starts at t equals 0 and it ends at t equals 3 times 10 to the negative 3rd seconds. What we have to do is put those in their boundaries, 0 and 3 times 10 to the negative 3rd seconds. And the force function, the thing that we're integrating is this thing here. So 0, 3 times 10 to the negative 3rd, 6 times 10 to the 6th t, minus 2 times 10 to the 9th t squared d. Okay? And it looks scary because of all the scientific notation, but it's not. You've got the integral of t and the integral of t squared, and those two things are really easy to do. So you end up getting, a delta p equal to times 10 to the 6 times t squared over 2 minus 2 times 10 to the 9 times t cubed over 3, all evaluated from 0 times 10 to the, 0 to 3 times negative 10 to the negative 3. And so then you just have to plug in properly your upper bound and your lower bound and subtract. And what you get for that is 9. Okay, so the answer to 37A is 9. And the units are kilogram meters per second. 37B is asking for the average force on the ball from the player's foot during that time of contact. Okay, well the average force is like you're kind of assuming that if I were to instead apply a constant force the whole time, what would the constant force be? Well, the average force is equal to the change in momentum over the total time. Right, just like average velocity is total displacement over total time, average acceleration is change in velocity over time, average force is change in momentum over time. It's the non-differential form of this equation that we learned yesterday. So the average force, sometimes we write AB over it, I'll do both just because. The average force is equal to this change in momentum divided by the time, 3 times 10 to the negative 3. And when you do that, you get 3,000. So the force average is equal to 3,000. The next part is asking you, instead of the average, what is the maximum value of the force? Okay, what is the maximum value? There are a couple ways that you can do this. I imagine all of you running to your graphing calculators and doing it that way, which you totally can. It turns out you could graph the function and just find the maximum value. But I want to do it using calculus because I love calculus and also. So when you maximize any function, you want to take the derivative of it and set it equal to 0. That's how you maximize. Okay, so if we have this force function, which is equal to 6 times 10 to the 6th t minus 2 times 10 to the 9th t squared, and I want to take the derivative of it and set it equal to 0, I get 6 times 10 to the 5th minus 4 times 10 to the 9th t equals 0. And then I can solve for t. And interestingly, the t value is exactly halfway through the t is 1.5 times 10 to the negative 3. This is the time at which the force value is at its maximum. So then you take your t value and you plug it back into your force function, and you get 4,500 newtons. So the maximum value of the force is 4,500, whereas the average value was 3,000. Okay. And then the last part of the question says what is the ball's velocity immediately after it loses contact with the player's foot? Okay, well the impulse or the change in momentum that we found was 9. Okay, well that means that 9 is equal to mv final minus mv initial, where the initial velocity was 0, so 9 is equal to the mass of the ball, 0.45 times the final velocity. So the final velocity is 20 newtons. Okay. Okay. So, moving along here. Let's do number 51. Number 51 is kind of a two-parter. And it says you have a 3.5 gram bullet is fired horizontally at 2 blocks at rest on a frictionless table. The bullet passes through block 1, which has a mass of 1.2 kilograms, and embeds itself in block 2, which has a mass of 1.8 kilograms. The blocks end up with speeds of 0.63 and 1.4 meters per second, respectively. Find the speed of the bullet as it leaves block 1 and leaves block 1 and enters block 1. So what you're looking for is the initial velocity of the bullet before it enters block 1, and then the velocity after it enters block 1. Or exits block 1, sorry. So it's a two-part conservation of momentum problem. The momentum is concerned for the collision of the bullet, again for the collision of the bullet with block 2. So if we write out both conservation of momentum equations together, we can solve them individually. Okay. So the very first situation is that you've got a bullet by itself that has momentum to start with. So the momentum of the bullet to start with is the mass of the bullet times the initial velocity of the bullet. And after the bullet collides with and interacts with block 1, the total momentum of the system remains the same. And so once that happens, now we have block 1 moving with some velocity, but you also have the bullet moving with some final velocity after it leaves block 1. Okay? Both of these, there are lots of unknowns in this equation. So we have the mass of the bullet, 0.0035, times the initial velocity of the bullet, which is one of the things that we're looking for, equals the mass of block 1, which is 1.2, times the final velocity of block 1, which is 0.630, plus the mass of the bullet, 0.035, times the final velocity of the bullet when it leaves block 1. That's two unknowns. Can't solve it. One equation, two unknowns, can't solve it. However, now we can take this variable, and that can become our initial velocity for the second part of the problem. So what you have, final velocity of the bullet now is going to be the initial momentum of the system as the bullet enters the second block. So if we consider our system now to contain the bullet post block 1 and pre block 2 and block 2, then we still have only 2 objects contained in our system. So the initial momentum of the new system is the mass of the bullet times the final velocity when it left the first block. And then afterwards, it's a perfectly inelastic collision, which means that they're combined, they move together as one, and they have a total mass of the mass of the bullet plus the mass of block 2 times whatever the final velocity is of block 2. So in this case, it's 0.0035 times the final velocity of the bullet equals 0.5 plus 1.8 times 1.5. I can solve this directly. And with this one, I get 721.4. Once I get that, I can plug it in up here and solve for this initial velocity. And with that, I get 937.4. So it's a tricky way to go about doing the problem, but once you realize that it depends on how you define your system, and momentum is conserved for this system and the system as a whole, before and after the entire thing, then it's a little bit easier to do the problem. Okay, the next one that I want to just briefly talk about is number 52. Number 52 is a conservation of momentum problem, but it's also a conservation of energy problem. 52 is one of those reasons why we didn't take a test on energy yet, because momentum and energy are very often interconnected. So you've got this situation where you've got a bullet that's entering a block, and then it exits the block, but it gives the block some of its momentum. And the question's asking, how high does it go? Well, once you figure out the velocity of the block after the collision using conservation of momentum, then you can figure out how high it goes using conservation of energy. Okay, all of its kinetic energy that it was given by the bullet will now be converted into potential energy. And for that, I got 0.073 meters or 7.3 centimeters. And if you want to see the work on that, you can look at the solution. Okay. Number 61 is the last question on the homework, and I will go through it in its entirety. So it says, a cart with mass 340 grams moving on a frictionless linear air track at an initial speed of 1.2 meters per second undergoes an elastic collision with an initially stationary cart of unknown mass. After the collision, the first cart continues in its original direction at 0.66 meters per second. What is the mass of the second cart, and what is its speed after? Okay, so you're looking for the mass, m2, and the final velocity of cart 2. So we have m1, which is 0.340 kilograms, and v1 initial, which is given to you as 1.2, and v1 final, which is given to you as 0.66, and then m2 initial is 0. Okay, m2 initial is at rest. And there's a picture, you can look at it because you're all following along in your book. And so this is conservation of momentum, right? So you do the same thing as always. Initially, only cart 1 has momentum. Its momentum is, and after the collision, they both have momentum. And so the momentum would be m1 times its final velocity plus m2 times its final velocity. But the problem is we don't know, and we don't know. We have 2 unknowns, okay? And that's where it's nice to have extra information. The extra information that you have in this problem is that it's an elastic collision. And so it's not just like, oh, that's interesting to know. That means you have to mathematically use that. And the way that you do that is to also write out another equation. This is momentum, okay? The other equation is conservation of kinetic energy. That's how we define what an elastic collision is. If it's elastic, that means kinetic energy is conserved. So the total kinetic energy before the collision, which is 1/2 times the mass of part 1 times its initial velocity squared, is equal to the total momentum sorry, did I say momentum? I meant kinetic energy, is equal to the total kinetic energy after the collision, which is the kinetic energy of part 1 plus the kinetic energy of part 2. And that's messy, right? Especially with these kinetic energy situations where you have all these squares. It gets to be an algebraic nightmare. But you guys are good at algebra, so it's no problem. The first thing I would do in a situation like this is cross out all the 1/2, because if kinetic energy is conserved, what we're writing out in each term is 1 mv squared, so each one has a 1/2. And then the next thing I would do is come up with a strategy for solving the system of equations. To me, the easiest strategy to use in this particular situation is to solve the top equation for M2 and to plug that into the bottom equation. Okay, so if I solve the top equation for M2, I'm going to subtract 0.340 times 0.66 to the other side and then divide by V2F. So here I get M2 equals 0.40 times 1.2 minus 0.340 times 0.66 all over V2F. And then I'm going to take this whole thing and I'm going to plug it in here for M2. Okay? So then you get 0.340 times 1.2 squared equals 0.340 times 0.66 squared plus, and then this whole mess here, 0.340 times 1.2 minus 0.340 times 0.66 over V2F times V2F squared. And you have now a V2F squared in the top and a regular V2F in the bottom. And so I can cancel this one with one of these, and now I have a linear equation that I can solve for V2F. Once I find V2F using this equation, I can plug it in up here and solve for M2. And so it's not like super, super easy algebra, but it's doable, and I know you can do it. So I'm not going to finish the rest of this problem mathematically, but I know that you can figure that out. You're going to encounter a lot of systems of equations in this momentum unit, and so you should practice and get good at it. So don't just say, oh yeah, I can do that. You should actually do it and get the answer. Okay. So if you're feeling like you're really struggling still with momentum, there's a video that if you want to kind of start at the beginning again, I videotaped my conservation of momentum lecture to my honors physics class. And I think that if you feel like everything got a little bit too difficult, a little bit too quickly, then you should go watch that honors physics lecture and give yourself a solid foundation before you try to move on to the next thing. It's on the honors physics website, on my website, and if you just kind of skip the going over the homework part of it, the rest of it is pretty good. And I do more examples, and it goes a little bit slower, and I think it's a good way for you to make sure that you really have the solid foundation that you need. So let's just remember that that's there, and if you're really struggling, go. Okay? We're going to take some notes now on conservation of momentum, but in 2 dimensions. And it's really the last, we have one more tiny thing that we have to talk about, but it's the last major part of this unit that we need to discuss. So conservation of momentum is true in 1 dimension, and it's also true in 2 and in 3 dimensions, as you can imagine. And when we have things that are vectors, we follow that you don't mix your x's and your y's. And that's absolutely still true when we talk about conservation of momentum in two vectors. So two-dimensional conservation of momentum is the same as one-dimensional conservation of momentum, except you have to do it twice. You have to do conservation of momentum in the x direction and conservation of momentum in the y direction. And the difficult part comes in that you're doing everything twice, but also in that very often you have to deal with vectors, momentum vectors, or whatever. And so I guess the easiest way to do this is to start with examples. So let's do a couple of examples and then you'll practice on your own, okay? Let's say that you have two objects that are coming at each other, but perpendicular to one another. So let's say you've got one that's going this way and one that's going this way. They collide. After the collision, the two objects stick together and move together. Okay? So let's call this one object 1 and this one object 2. This one has mass of 1 kilogram and this one has mass of 2 kilograms. And this one has an initial velocity is meters per second in the x direction, and this one has an initial velocity that is 4 meters per second in the y direction. And so my question for you is, what is the magnitude and the direction of the final velocity of those two objects after they have stuck together? Magnitude and direction of the final velocity. So I want you to describe the vector completely. Now, when I ask for magnitude and direction, that's two things, right? And two things requires two equations. And the two equations that we're going to use in this are conservation of momentum in the x direction and conservation of momentum in the y direction. Okay? One thing that you know sort of intuitively and from just like life experience is that these two things are going to collide and then they're going to go off kind of this way, right? That has to be true because the net total momentum is this way and this way, right? And so what that means is somehow they're going to go off in this direction into the first quadrant, okay? And so the question is, what is the angle and what is that final velocity? They're going to stick together, okay? The two objects will stick together. So if we do this, then we'll do a conservation of momentum. Net momentum initially in the x direction is equal to net momentum, finally in the x direction. And then net momentum initially in the y direction is equal to net momentum finally in the y direction. So it's the total momentum is conserved in each direction individually. So then you ask yourself the question, what is the momentum or what has momentum in the x direction to start with? And that is this one here, right? So that's going to be m1 v1 initial equals. And then after the collision, they stick together. It's perfectly inelastic, which means that after the collision, the momentum is going to be one object that has total mass m1 plus m2. And then there's going to be some final velocity, but we're only finding the x component of that final velocity, right? What we're finding is this part of the momentum to start with. This is my vx final and my vy final. And if I'm using conservation of momentum in the x direction, then the only part of that I can find is the x component of that velocity, right? So then I can plug in my numbers and I can say, okay, 1 times 7 equals total mass, which is 3, times my final velocity in the x direction. So the final velocity in the x direction is 7 meters. Okay. How about in the y direction? I can do the same thing. The total momentum in the y direction is just the momentum of the object that's moving in the y direction. This is the only thing that has momentum in the y direction. This one only has momentum in the x. This one only has momentum in the y. So for the y component, it's going to be m2 times v2 initial is equal to, and then the same thing, they stick together, right? So their total masses afterwards times the final velocity now in the y direction. So this will be 2 times 4 equals 3 times vfy. So the final velocity in the y direction will be 8. So this is 7/3 and this is 8/3. And so you can probably figure out the hypotenuse and the angle or the magnitude and direction of the velocity vector after the collision. Okay, and you can do that on your own. This is the most simple type of conservation of momentum in two directions, because each one of these didn't really have initial components per se in the x and the y direction. If we do another example of conservation of momentum in two dimensions, it's going to be a little bit trickier. Let's say instead that you have two objects that are coming at each other like so, and they collide. Okay, let's call this object 1 and object 2. M1 is 2 kilograms and M2 is 6 kilograms. And they're coming at each other. This one has an angle of 45 degrees, and this one has an angle of 30 degrees. They're coming at each other from different directions with different velocities, different angles, different momentum, everything. And then they bounce off each other. So it's inelastic, but it's not perfectly inelastic. And what happens is M1 bounces off at an angle of 20 degrees. And it bounces off with some velocity that we don't know. So we'll call it V1. And this one bounces off and actually goes this way, which is an angle of 10 degrees, with some final velocity. Okay, so what happens is incoming, bounce off, outgoing. Okay. Now my question for you is, what are the two final velocities? What is v1f and what is v2f? What are the magnitudes of those two things? So same thing, we have two conservation of momentum equations, and the way you go about doing them is the same, but the difficulty level is different now. Okay, because each one of these initial momentums for each one of these objects now has two components. It's got an x component and a y component for M1, and an x component and a y component for M2. Okay, and so you have to deal with those and consider that they both have momentum in the x direction to start with, and they both have momentum in the y direction to start with as well. So if I'm going to do my conservation of momentum in the x direction, it's going to be that they're both going to the right to start with. So it's going to be M1 times V1 initial times cosine of theta 1, which is 45 degrees, plus M2 times V2 initial times cosine of theta 2. They both have x components, but they're both moving to the right. This is my total x momentum to start with. My total x momentum to end with is going to be something similar, where I have to write things in terms of their angles, right? And so we should even be more specific with our labels: theta 1 initial, theta 2 initial, theta 1 final, theta 2 final. So after the collision, it's the same. Basically, they're both moving to the right, but my one initials have become one finals, and my two initials have become two finals. So now it's M1 V1 final cosine theta 1 final plus M2 V2 final cosine theta 2. And yeah, it looks terrible, but there are numbers, right? We can plug in lots of numbers. But you will notice that you cannot solve this directly. Okay, there are two unknowns, V1 and there's equations right now. So what we need is to now solve the y equation as well. Okay, and so if we look right now, what we see is that one of these objects has a negative y momentum to start with, and one has a positive y momentum to start with. And you have to consider that. The direction has to be considered. So M1 has a negative momentum to start with in the y direction. So we'll say it's negative M1 V1 initial sine theta 1 initial plus the upward momentum of M2, M2 V2 initial sine theta 2 initial. And then after, they have momentum in the opposite direction. So now M1 has a positive momentum. So it's M1 V1 final cosine, sine of theta 1 final minus, arrow down, V2 final sine of theta 2. Now this sucks, right? This is terrible. But let's just plug in our numbers and see what we get. Okay, so M1 is 2 kilograms. V1 initial, oh hey, I did not give you those numbers. Let's say V1 initial is 2 meters per second and V2 initial is 1 meter per second. So M1 V1 initial is 2 times 2 cosine of 45 plus M2 V2 initial, which is 6 times 1 cosine of 30 equals M1 V1 final, which is 2 V1 final cosine of 20 plus M2 V2 final cosine 10. So I wrote this on 3 lines, and I apologize for that. But what you can see is a lot of this stuff starts to get a little bit easier. If I simplify this, M times cosine of 45. Cosine of 45 is square root of 2 over 2. Right? So this actually is 2 square root of 2. Plus 6 cosine of 30 is square root of 3 over 2. So it's 3 square root of 2 equals 2 cosine 10 plus 6 V2 final cosine of 10, which I also don't know. So this is one equation. Okay. Oh, and nice. This actually turns into 5 square root of 2. Perfect. Now let's do the same thing for this equation over here. So what we get is, for the y equation, negative 2 times 2 times sine of 45 plus 6 times 1 times sine of 30 equals 2 times v1f times sine of 20, 6 times v2f times sine of 20. Now, same thing here, sine of 45 is square root of 2 over 2, so we get negative 2 square root of 2 plus.
Good afternoon, Nancy. Good afternoon, Allison. Tomorrow is Battle of the Sexes.
Plus 6 sine of 30, where sine of 30 is 1/2, so it's really 6 times 1/2, which is 3, equals 2 v1f 20 minus 6 v2f times 10. Okay, well that's still pretty terrible, but we can now solve for one variable and then plug it into the other one, into the other equation. And let's solve, for example, let's solve this one for, okay, there's any really nice, easy way to do it. But if I solve this for v1f, I get 5 square root of 2 minus 6 v2f cosine 10 equals, divided by 2 cosine 20 equals v1f. Then I can take what this is and plug it in here for v1f. So I get negative 2 square root of 2 plus 3 equals 2 times 5 square root of 2 minus 6 v2f cosine of 10 over 2 cosine of 20 times sine of 20 minus 6 v2f sine of 10. And then this is pretty messy, but you can simplify it a little bit, and we should definitely do that. So the 2's here cancel, 2 and 2, and then the sine of 20 and the cosine of 20 we can write as tangent of 20 when we rewrite the whole thing. So let's do that. Negative 2 square root of 2 plus 3. Whoa, where did that come from? Oh, just kidding. Equals 5 square root of 2 tangent of 20 minus 6 v2f cosine of 10 tangent of 20 minus 6 v2f sine of 10. Now we have v2f and v2f. So we want to get the tangent of 20 thing on the other side. So negative 2 square root of 3 plus 3 minus 5 square root of 2 tangent 20 equals v2f times the quantity negative 6 cosine 10 tangent 20 minus 6 sine 10. And then I can divide everything by this term here. Negative 2 square root of 3 plus 3 minus 5 square root of 2 tangent 20 over negative 6 cosine 10 tangent 10 minus 6 sine 10 equals v2f. And then once I find this, which is just a number, and the only reason I haven't plugged it in is because I don't have a calculator. This is just a number. Once I find this, I can plug it into this equation and solve for v1f, and then I have those. So this is kind of, I won't say it's as bad as it gets because then you'll yell at me later, but it's one of the more difficult two-dimensional conservation of momentum problems. And it's not because the problem itself is difficult to understand, it's because the algebra is hard. Okay, and so it's just going to take, you have to be sort of careful, and you have to be organized with your algebra, and you have to know how to solve this. Okay, so you have some homework problems which are on the board, and I will have solutions for you on the back, and you can work on that homework. It's due on Thursday. Thursday.